Hello students, so now we come to the third and the last part of the numericals of this chapter, work, energy and power, that is the 2C exercise. Here in this, we will be using the formulas which we have studied in the previous part of it. All the kinetic energy, potential energy will be used, but what you should remember here, we will be applying the law of conservation of mechanical energy a lot. That is the kinetic energy which it will be there at the bottom, and if it is thrown upward, it will be equal to the potential energy at the maximum height. And during its journey from going from down to up, or from the highest point to coming to the ground, remember at any instant the total energy is going to remain the same. Okay, that is the sum of kinetic and potential will remain the same. So with these concepts we'll be doing the third part. There are very few numericals here, so let us see it one by one, starting with numerical number 1. A ball of mass 0.2 kg is thrown vertically upwards with an initial velocity of 20 meter per second. Calculate the maximum potential energy it gains as it goes up. So when we need to know the maximum potential energy, it means it is the highest point. So at the highest point, whatever was the initial kinetic energy will get converted to potential energy. So this concept only we will apply here. So maximum U will be equal to the kinetic energy which it was having initially. So if I give a subscript initial kinetic energy and apply the formula half mv square. So half, the mass is 0.20 kg, I will write 0.2. Velocity is given as 20, so 20 into 20. So I will first cancel this. 0.10 in 0.2 into 10 gives me 2, and 20 is 40 joules. Now let us take a look at numerical number 2, which says a stone of mass 500 gram is thrown vertically upwards with a velocity of 15 meter per second. Calculate the potential energy at the greatest height. So it is like the previous sum only. Okay. Then the kinetic energy on reaching the ground. So when it reaches the ground, what is the kinetic energy? Whatever was the initial kinetic energy, that only will be the kinetic energy when it reaches the ground. Or to say whatever was the potential energy at the highest point will be equal to the kinetic energy on reaching the ground. Okay. And then the total energy at its halfway point. Here you have to be very careful. As I told earlier, total energy during its journey is going to remain the same. So whether it is halfway point or 1/4 or 3/4, whatever place, total energy will remain the same. That is, whatever is the initial kinetic energy or whatever is the potential energy at the maximum height. So based on these concepts, let us do it. So first of all, it is told the potential energy at the greatest height. So at the greatest height, the potential energy will be equal to kinetic energy, and kinetic energy formula I write half mv square. Half, so half is written, mass is given to us as 500 gram. So 500 by 1000, and the velocity is 15. So I cancel this 500 twos are. This will give us 7.5. This will give us 7.5. So now 7.5, 7.5 ending with 5. So 5 square is 25. And after 7 comes 8. So 7 8s are 56. Okay. This much joule you get it. So this is the potential energy at the maximum height. Now in the B part, what is asked? The kinetic energy on reaching the ground. So kinetic energy on reaching the ground will be the potential energy at maximum height. So K at ground will be equal to the potential energy at maximum height. So we know the potential energy at maximum height. So we get that as 56.25 joules, the same answer. Okay. Now the C part, the total energy at half the way. So whether it is half or 1/4 or 3/4 or 1/5, whatever, it will remain as the total, the kinetic energy which it was having at the ground level, or the potential energy at the maximum height. So I will write here in the C part, total energy at halfway point is equal to u at maximum height, so which is 56.25 joule. So very good numerical to get your concept clear about how much total energy is there at any of the position during its journey. Let us take a look at numerical number 3. A metal ball of mass 2 kg is allowed to fall freely from rest from a height 5 meters above the ground. So a metal ball is falling, mass is given, height is given. We have to take g as 10 meter per second square. Let us see what we have to calculate. The potential energy possessed by the ball when it is initially at rest. It is at rest at a height of 5 meters. So there we have to find what the potential energy is there. Direct formula. The kinetic energy of the ball just before it hits the ground. So you know what we have been doing in the last two numericals. So when it hits the ground, kinetic energy will be equal to the potential energy at the initial position. Then what happens to the mechanical energy when the ball hits the ground and comes to rest? So it hits the ground and comes to rest. You know, when it hits the ground, there will be sound produced. So it means sound energy it is getting converted to, as well as there will be a small amount of heat generated. So that potential energy is getting converted to sound energy and heat energy. Let us do the numerical part of it. So first of all, we have to calculate the potential energy. So we write the formula U equals to mgh. So mass is given to us 2 kg, g is 10 and the height is 5. So that gives us 100 joule is the A answer. A of the answer is 100 joule. We are getting it. Now in the B part, in the A first part, this was there. Okay. Now the B part, the kinetic energy of the ball just before it hits the ground. So we will write here kinetic energy here will be equal to the potential energy, and so the answer will come as same 100 joule. Okay. Now the B part of it, what happens to the mechanical energy after the ball hits the ground and comes to rest? As I told, it will get converted to sound and heat energy. So I will go to write here the mechanical energy gets converted to sound and heat energy. So you understand here about energy conversion also, which is a very important part. We need to know the energy conversions in many devices. Here also you come to know it is converted to what energy. We come to the fourth numerical now. It says a person swings on a rope from a cliff that is 20 meter high. So he's using a rope, he's swinging, coming down from a cliff which is 20 meter high. How fast is the person moving at the lowest point of the swing? So it means lowest point means he's covering 20 meter. So when he has covered 20 meter, what is the speed with which he is coming? Okay, that we have to find. So whatever potential energy with which he started at the topmost point will become his kinetic energy at the lowest point. So we'll be applying this concept only. So we write here kinetic energy will be equal to potential energy. For kinetic energy, I write half mv square, and for this I write mgh. Remember, the person is the same, entire thing is same, so the mass remains the same. So m is cancelled from both the side. Half is written, we have to find v, so v square. G is 10 and height is given as 20 meter, so we write here 20. So we get here v square, this 2 will multiply with 10, it will become 20 into 20. So v is equals to root over 20 into 20, we get it as 20. Speed is asked, meter per second. So again applied law of conservation of mechanical energy to work out this sum. So let us take a look at numerical number 5, which is a diagram based sum and is a very interesting numerical. It says the diagram given alongside shows a ski jump. A skier weighing 60 kgf stands at A at the top of the ski jump. He moves from A, takes off his jump at B. So he comes from here and then jumps like this from the point B. Calculate the change in gravitational potential energy of the skier between A and B. So this is the point A, this is the point B, change in gravitational potential energy. So you'll be taking the difference in the height and calculate the potential energy there. And then it says if 75% of the energy in part A becomes kinetic energy at part B. Now whatever is the potential energy here, this part A, not this point A. 75% of that will be getting to converted to kinetic energy at B, and we need to calculate the speed of the skier when he arrives at B. So let us see what we will be doing it. First part, let us calculate the change in the gravitational potential energy. So the A part. So for that, first of all, you need to take that height difference. So I will write here h is equals to 75 minus 15 equals to 60 meter. So I will write change in potential energy, okay, between A and B is equal to mgh. So 60 kgf is the weight given. I can take the mass as 60 and g value as 10. So 60 into 10, and the difference in the height we have got 60. So 6 6 is 36, and then 3 zeros give me the change in the gravitational potential energy. Then follow what it says here. If 75% of the energy in part A, so part A energy we have got, 75% of that will become kinetic energy at B. So I can go to find the kinetic energy at B will be 75%. So 75 by 100 into 36000. This is the energy. So I know the kinetic energy at B is this much. I need to know the speed there. So for kinetic energy, I will write half mv square is equals to the same value. I will just copy it now. Now half m is 60, then v square 75 into 36000 by 100. So I will get here v square equals to 75 into 36000 into 2 will come from here, and 60 will come down, and here 100. So we can solve it out now. I will just cancel this 20 here is 10 cancelled. I can cancel this 6 6 is 36. So I will be getting v equals to 75 into 2 will give me 150, and 15 6 is 90, and a 0 of 150. So root 90 is 30. So I will get here the speed of the skier at the point B to be as 30 meter per second. Hope you have understood this somewhere some part of the energy gets converted, and if it is given in percentage, how to relate and find it out. Now let us come to numerical number 6. Numerical which needs to be understood properly. It is based on percentage part also here. A hydroelectric power station takes its water from a lake whose water level is at a height 50 meter above the turbine. So where the turbine is placed, water level is 50 meter above it, assuming an overall efficiency of 40%. So the pump which will be there, okay, that is having a efficiency of only 40%. Calculate the mass of water which must flow through the turbine. So how much water should flow through the turbine, okay, so that in each second to provide a power output of 1 megawatt. So we should get a power output of 1 megawatt. So how much of water should flow through the turbine to produce that? So first of all, we will relate that power. So power output is given to us. So that is given as 1 megawatt. So that 1 mega is 10 to the power 6. So 10 to the power 6 watt. Remember, this is power output. So first of all, I will go to find the potential energy because it is based on height. So I should know the potential energy here. Okay. So the mass of water we have to find. We will keep that mass to be as m. So formula written first, then m. G is 10 and the height is 50 meter. So we get it here as 500 m. Okay, means m is the mass there in terms of joule. This is the potential energy, and the time given to us is each second. So I can find power, okay, as energy by time. So energy here is 500 m and by 1. So this is the power which is there, but the output will be only 40%. So I am writing here power output. So power output will be 40 by 100 into 500 m. And this power output is given to us as 10 to the power 6 watt. So I am going to write here, this much is the power output, 40 by 100 into 500 m. So I have to calculate m into 100 comes here. 40 and 500 is equals to m. So let me cancel this zeros here. So these three zeros are cancelled. If I take here 520 is 100. 4 5s, so I am getting m is equals to 5 here and 1000 here. So we get here 5000 kg, that is this much mass of water should flow through the turbine to get a power output of 1 megawatt. I hope you have understood how to work out numericals like this. We move on to numerical number 7, which is based on a pendulum. It says the bob of a simple pendulum is imparted a velocity of 5 meter per second. So the pendulum is given a velocity of 5 meter per second when it is at the mean position. So remember, a pendulum, this is the mean position and these two are the extreme positions. At this place, the speed given is 5 meter per second. To what maximum vertical height will it rise on reaching to the extreme position? So from mean it is going to the extreme position. So to the what maximum height it will go. Okay. And then it is told if 60% of its energy is lost in overcoming the friction in air, 60% of the energy is lost. So you have useful energy available. 100 minus 60 is equal to only 40%. It means the 40% of this kinetic energy will be getting converted into the potential energy at the extreme position. So you will be applying this. So taking into that percentage part, first of all, I will be taking the useful energy and mention it. So useful energy here is 100 minus 60 is equals to 40%. So 40% of the kinetic energy at the mean position will become equal to the potential energy at the maximum height. So I will be using this. So I will write here 40% of kinetic energy will be equal to the potential energy at the extreme point. So now 40 by 100 into kinetic energy half m v square and then here mgh. Remember, it is the same pendulum bob, so the mass is going to remain the same. So let us cancel out this mass. And so we need to find the h value. So let me put down the values first. Half m is already cancelled. V is given here as 5. So I will go to write here 5 square is equals to g is 10 and this h I have to calculate. So 40 into 1, if I remove 5 and 5 and 100 here and 2 here, this will come down as 10 is equals to h. So let us calculate it out. Okay. So if I cancel this 0, 4 25s are 5 5s are, this is cancelled, this is cancelled. So you are left with h is equals to 1 by 2, that is equal to 0.5 meter. So this is your answer. It means at the extreme point, the height from the mean position will be 0.5 meter. So relate how to relate with the useful energy which is given there in the question. Finally, we come to the last numerical of this C part, or to say the last numerical of this chapter, work, energy and power. Let us take a look of this numerical which is based on a pendulum. The figure alongside shows a simple pendulum of mass 200 grams. So the bob has a mass of 200 gram. It is displaced from the mean position A to the extreme position B. The potential energy at position A is 0. This place potential energy is considered to be as 0. At position B, the bob is raised by 5 meter. So at B, it is at 5 meter from this mean position. So this becomes our height to say if we have to find the potential energy, and we have to. A part, what is the potential energy of the pendulum at the position B? What is the mechanical energy at C? C is the point somewhere in between A and B. What is the total mechanical energy? So again, remember, total mechanical energy during its entire journey will be the same, and it will be same as whatever is the potential energy at the maximum height. And then what is the speed of the bob at position A when released from position B? So when it is released from here, what will be the velocity or the speed it will be having at this place? So let us work it out. So A part of it tells us to find the potential energy of the pendulum at position B. So potential energy at B, mgh. M is 200 gram, so 200 by 1000 into G is 10, and the height here is 5. So 2 zeros, 2 from here, 1 cancelled, 2 fives is 10. So the potential energy at this extreme position B, we have got as 10 joule. What is the total mechanical energy at the point C? So I will write here total mechanical energy at C is equals to the potential energy at maximum height, which was B. And how much was it? It was 10 joule. So we get the answer for this part also, B part. And now let us see what the C part is asking us. What is the speed of the bob at position A when released from position B? So from where here it is released, it comes here. So whatever is the potential energy at B will become the kinetic energy at A. So I am writing kinetic energy at A is equals to potential energy at B. I write half mv square, the formula, and here mgh. M is cancelled, so I get here half into V square. V we have to find, G is 10 and the height is 5. So V square will be equal to 2 will go and multiply with 5 as 10. Another 10 is already there. So I will write it as root over 10 into 10. That gives me 10 meter per second. So this is your answer for the C part. I hope you have understood this numerical. We come to the end of this numerical of part C as well as of the chapter. Hope my explanation of these sums has helped you to understand the numericals. Work the numericals also on your own. Perfect yourself so that you perform well. Do remember to subscribe to my channel, like my videos, and Also put your comments. Thank you for watching.